Anytime, just
All right, everybody, I think we're going to start the seminar now.
I started to start lecture a couple minutes late too. I think people are still getting used to like showing up in person for things, right? As opposed to just clicking on a Zoom link. Well, actually, that quieted everybody down with my voice.
just saying Zoom.
Yes, so let me go ahead and get started here. So it's my pleasure today to introduce Claire Mundy, who's going to be presenting her master's work, sort of as her, kind of requirement for her master's degree. Claire joined my group during the pandemic, the fall of 2020. Before that, she was originally from New Jersey, and she did her undergraduate in physics and geosciences at Skidmore. And her interest in atmospheric science kind of developed from an REU that she did at Scripps, where she was analyzing ground-based LiDAR data over Greenland. And so she expressed some interest in her statement when she applied here of working on Arctic-related problems. And John and I had a project funded right around the same time to look at the role of summertime cyclones in reducing sea ice, both the role of radiation and also the mechanical effects of the wind. And so the timing was great. Claire came, started working on this project, also with Ian and John. And I think she's going to present that work for you today. But before we get to that, I just want to add one more. I'd like to add just a personal detail about everybody. And so Claire told me that she enjoys experimenting with new vegan recipes. So if anybody here is interested in vegan recipes, Claire would be a good person to talk to. We actually have a Slack channel where we exchange recipes in the group between different group members, and also growing her plant collection. But today she's going to talk about her research on summer cyclones and their impact on Arctic sea ice.
Great, can everyone hear me? I don't think the mic is on.
Sorry.
Okay.
Should be good.
Okay, can everyone hear me?
Should be good. Yeah.
Can everyone hear me? I don't know if the mic is.
Can you hear her in the back?
I can talk a little loud. I'll just shout.
The mic's definitely on, because I can hear it tapping, but I can't hear you through the
Okay.
Can you click it away? Like, not way on top of like this.
Here.
Give it a try.
Can you hear me now?
Yeah.
Is that better?
That's better.
Great.
Yeah.
Okay, so thank you for that introduction. So yeah, I'll be talking about the impact of summer cyclones on Arctic sea ice today. And so just to kind of zoom out and start with sort of a broad overview, I wanted to talk a little bit just about Arctic climate and the role that sea ice plays. And so first on the left here, we have two plots showing temperature anomalies. The top one is global temperature and the bottom specifically for the Arctic. And so you can see in the top plot that the temperature has changed about 1 degree over the past 150 years. And then in the bottom plot, we can see that in the Arctic more specifically, that temperature has been amplified about 4 times, and there's a temperature anomaly of about 4 degrees. And so that overall just kind of summarizes the effects of Arctic amplification and how the Arctic is warming faster. And sea ice plays an important role in that, which you can see in the right plot here, which looks at sea ice extent anomalies over the past 50 years or so. And so while the March extent, shown in the black curve, hasn't changed super much, the September sea ice extent has a much more intense decline over this time period. And so both of these, the temperature and the sea ice extent, kind of go hand in hand, looking into sea ice feedbacks. And so on the left here is kind of a simplified view of a traditional sea ice feedback, where the increase in temperature, which we saw in that first plot, will lead to frozen surfaces melting and revealing darker surfaces, reducing the albedo, increasing absorption, which then of course feeds right back into our increase in temperature. And that's demonstrated in these two true color satellite images on the right. The top one taken in about mid-April, and you can see it's almost entirely ice covered, very bright just looking at it, especially in comparison to the bottom plot, which was taken in late July. It's overall just a darker image. A lot more of the darker ocean is revealed And so you can see how that will play into even furthering, reducing the extent of the sea ice, which is evident kind of along the left-hand side there. And so the question that we're asking kind of in this project is how intense cyclones can kind of play into this feedback. They can either enhance it by, reducing ice even more, playing with some of these radiation effects, or they can help stabilize this mechanism by either slowing the ice melt and, again, either enhancing or reducing the incoming radiation. And so currently, the jury's still kind of out on exactly what we can expect from these Arctic cyclones. And so I have here just two summary figures from recent papers that compare what they're calling cyclone days where cyclones are evident in sort of their records here versus non-cyclone days, which is kind of just an average of everything else. And so we have on the left here this first paper by Timothy and Doyle, 2021, showing in August there is a very kind of dramatic, especially one lag day after the storm passes, decline in sea ice area. I will also mention that these error bars are kind of relative to the average climatology, so anything outside of them is showing sort of an enhanced melt outside of what you would expect in September. And so this paper does show kind of a localized intense sea ice loss as the cyclone passes. But an earlier paper, Scriber and Serez 2020, is showing kind of the opposite story, where across the Arctic over the summer months, June, July, and August, we see an increase in sea ice concentration, which is kind of counter to the other paper. And so there are a lot of these different effects that we can anticipate seeing. And so for the rest of the talk, I'll be describing the approach I'm taking during my master's here to sort of address this kind of discrepancy. And so we asked two main questions. The first is, what do observations tell us about the mechanical impact of storms? And secondly, is this mechanical effect enhanced through cloud radiative effects? And so in order to answer these questions, I just really briefly want to step through kind of the data I used to answer these. So first, in order to sort of first identify storms and then discuss their sort of area of impact, we used reanalysis data from ERA 5, and we defined the storm duration as when the storm pressure is less than 984 hectopascals. So this is just an example of one of the case studies I'll be showing, kind of at its beginning starting to develop kind of in the Bering Sea on the right side of the plot. And then next for sea ice concentration, we used passive microwave data, a product from the National Snow and Ice Data Center, showing daily average sea ice concentrations. And then we defined something called the marginal ice zone, and this is consistent with a lot of previous work, between sea ice concentrations of 15 and 80%. And so this region here is where we would expect to see a lot of change. This is where the ice is at its thinnest and most vulnerable to all these different effects that I've been talking about so far. And then next we have the wind data, which also came from reanalysis. And for the next few variables, despite being on a kind of smaller grid at hourly, we averaged it to the same grid as the sea ice concentration to provide a more direct comparison. And we did daily averages as well to kind of do that more direct comparison. Next, for sea surface temperature, we used a product from NOAA. And again, we took this and interpolated it to daily averages on the same sea ice grid, kind of for, again, a more direct comparison. And then in order to look at cloud effects, we used data from CloudSat and Calypso, both of which are satellites in the A-train, shown on the left. And so CloudSat carries a cloud profiling radar, just shown in the top there, in order to get a vertical profile of the cloud structures as it flies over pass. And then similarly, Calypso carries a LiDAR, which gets a fairly similar picture, but picks up more on kind of your smaller ice particles along the edges of clouds. And then together, these two products can be used to define other variables such as cloud phase, cloud rate of effect, and looking into precipitation effects as well. And so now we can begin combining all these different data sources to begin looking at Arctic cyclones kind of in their entirety. And so for this talk, I'll be looking at two specific case studies, the first of which is this August 15, 2010 case. And so on the left, we have a true color kind of animation of the storm kind of as it evolves. And you can see just by watching through, there's this very well-defined cloud structure as it evolves, particularly these 2 days. You can see the cyclone effect as well. And then on the right, I will say thank you to Ian for providing the figure on the right. You can see as well, kind of as it evolves, it's bringing a lot of this very moist air, which helps define the cloud edge, as in the left figure. Also plotted here is sea ice concentration. And if you watch this enough times, you can kind of see along the edge of the sea ice, there is sort of a visible retreat, especially looking closer around these islands. You can really watch and see how that sea ice evolves. And so our first step here was to kind of quantify that change. And so the first thing that we did was kind of define our storm impact area. And so that's here on the left. We used the 990 and 1000 hectopascal contours throughout the storm duration to define this area that we said would be impacted by the storm. So that's through its entire lifetime. And then we quantified just the amount of sea ice that's within that box. Oh, I will say also, so after we found the contours, then we bounded them by their minimum and maximum longitude and latitude, which creates this kind of trapezoidal box around those contours. And so we then sort of added up all the sea ice in that box for each day, and that is plotted on the right, starting at the beginning of the month all the way to the end, and the storm duration is shaded in that like blue-gray. And so the top plot is showing in blue the change in that ice. And we, alongside in orange, the sort of daily climatology. So that's the average from 2000 to 2019. And that's kind of what we would expect to see in that box if there wasn't an influence of the cyclone, just kind of averaged out. And so just looking at the top plot, you can see there's this dramatic decrease leading up to the storm, and you're losing a lot of ice as the storm kind of progresses. In the bottom plot, we have something that we've been calling the relative anomaly, which is the difference between the anomalies of the top two plots, and it shows kind of how much the cyclone is kind of impacted and changing relative to what you would expect in climatology. And so we see that throughout the whole storm, it's negative, and it doesn't really increase again and become sort of similar to what we would see in the climatology until about like a good week after the storm. And so to begin sort of attributing this loss and this large change in sea ice that we're seeing, this large decrease, I will say, to be specific, we first investigated the impacts of clouds. And so on the left here is just the true color image with the overpass going from low latitudes to high latitudes. And so on the top plot we have the radar reflectivity, and we can see these two very well-defined cloud heads, one referencing kind of the center of the storm here and one sort of the tail of the storm on the other side. And then beneath that is the estimate of cloud phase. And so there are a few like high-level ice clouds, and you can also see maybe a low-level liquid cloud kind of sort of center, but overall the clouds are primarily mixed phase. And then that plays into the next plot, the cloud radiative effect. And so the blue curve, which is your bottom of atmosphere long wave effect, is fairly consistent throughout the entire cross-section. And so that's your additional heating, so that's why it's a positive term of the cloud present, and adding that additional long wave term. But the one thing that's variable is your bottom of atmosphere short wave effect. And this is generally a cooling term, and this is where the clouds are reflecting the additional incoming radiation. And it starts off small along sort of the center of the storm, but as you get closer to where the ice edge is at your higher latitudes, that shortwave effect starts to dominate, and you see a net cooling effect as shown by the black curve. And overall, that doesn't really match with what we just saw showing the large decrease in sea ice. And then also just for completeness on the bottom, we have precipitation, and so there's a bit of a snowfall maximum kind of near the center of the storm. But again, as we move closer to the ice, the snowfall rate becomes small, and there's a little bit of rain mixed in. But again, these values are quite small and don't play a large role. And so we're starting to think now that clouds and precipitation are not going to be playing as large of a role as we thought in this storm, particularly because it just doesn't match up with the ice that we saw. So instead, we decided to look at kind of a more dominating factor of these cyclones, which is their wind effect. And so here, the daily winds for each day are plotted along with a daily difference in sea ice concentration between the 2 days listed in the title. And so just to start off very broad, in each of these different days, you can see there's the very standard cyclone. We've got an on-ice flow coupled with an off-ice flow. But what's more interesting is how these two different wind directions can show up in the ice field. I'm realizing now the blue's not super apparent on this projector. But overall, there is sort of this dipole effect. Maybe we can see it more on the second, where we have on-ice flow that's essentially corresponding with this decrease in sea ice concentration, and then coupled with an increase kind of in the lower bands here, where you have the off-ice flow. And so here we're thinking that the winds are kind of compressing this ice and pushing it, which is going to be corresponding to your regions of decrease. And then coupled with the off-ice flow, you're seeing an extent and an increase of ice area as the winds are pushing. And so what's even, and then sort of second to that, after we see this increase in area here, you start to see a decrease along the edge. And you can see, and then in this one, the ice turns almost all red, as after the ice was ejected, it begins to melt more. And so just to kind of summarize here, winds over the marginal ice zone that we were just looking at, what we did was averaged all the wind vectors over the ice. And so within this storm period, the shaded region, we can see that there's dominated by southward off-ice flow. And what this means is that we're kind of ejecting the ice, and we're hypothesizing that it's going to be ejected into warmer waters. And so that's what we did next, was decide to couple it with the sea surface temperature. Here we have the same plot, sea surface temperature in the marginal ice zones. And just as a brief note here, the marginal ice zone is not static. So this is just showing the temperature of the water where the ice is as it's sort of getting pushed around by these winds. And so through the storm duration, we see there's an increase in sea surface temperature that remains high even after the storm. And then the second plot is just the derivative of the top plot, just to emphasize these changes that during the storm we see the derivative maintaining positive and even increasing more after the storm has passed. And seeing how prolonged this increase in SST is, that matches up a lot better with the changes in sea ice area that we saw in the first plot, which was prolonged for almost a week after, just like these increased temperatures where the ice is maintained as well. And so just to summarize, sort of the mechanism that we're proposing in this first case study is that the enhanced southward winds along the marginal ice that we just quantified is what's ejecting the sea ice into warmer waters, and that's what's leading to the enhanced melt that we saw in our first time series of sea ice. And this result, again, is fairly consistent with the plot I showed earlier, where we do see these large melts. However, what we're seeing is much more of a prolonged effect here, because now the ice kind of is living and staying in this warmer water after it was moved, as opposed to this one, which the sea ice area seems to rebound a lot quicker. So now to offer a bit of a different, oh, yeah.
I'm sorry, just had a quick question. The hypothesis that the winds are affecting, transporting the ice, but would the ice move at a different angle relative to the winds just due to Ekman transport?
Possibly. I don't know much about Ekman transport, but I'm pretty sure that the winds being kind of the main driver, I feel like they would be very similar because the wind effect is so strong, especially compared to other forces like maybe like ocean currents and that kind of thing. So yeah, we're just thinking that's sort of the main component, and we are ignoring lots of other aspects so far. But, yeah. So now we're going to offer kind of a different perspective of looking at another case study that happened pretty much like a week after the first one, but now we're in a different location. And we can see as the storm's evolving, we're not necessarily seeing as well-defined as cloud head in this one. Again, in the plot to the right, there's sort of less of a frontal structure. We don't see as much of this moisture transport as we did in the first case. And looking again at the sea ice concentration, especially along the edge, it doesn't appear just from this one animation that there's as much of a retreat in this case as there was in the first one. And so to quantify this one again, we have our two contours for each day defining the storm area. And overall, this one does cover a much larger area than the first one, which only had that tiny little sliver. This one has a real impact on the ice. But as we go to quantify it, again, we're seeing a totally different signature, where the sea ice is definitely not decreasing as we would expect it, as the climatology predicts, but is instead almost increasing. And the relative anomaly shows kind of that similar story of starting out negative and becoming positive throughout the storm duration. And so as we go to look at the winds, we see now that the area along the edge here is actually dominated by northward pushing winds. So you have this very strong on-ice flow where the ice is located. Similarities too, you do have kind of your coupled decrease in ice as the ice gets pushed alongside your sort of increase in ice concentration on the flip side of the storm. But overall, along the marginal ice zone where the ice goes below, you do have sort of on-ice flow, which was then quantified. You can see throughout the storm duration, positive wind direction. And then couple that again with our sea surface temperature, we see pretty much the opposite signature in this case, where if we track where the ice is located, throughout the storm duration, the sea surface temperature is actually decreasing, as shown in the top plot, and then emphasized again with the negative derivative in the bottom plot. And so what we're thinking here is that now, because we have these enhanced northward winds interacting with the ice, we're ejecting the marginal sea ice into cooler waters. We're pushing it into these higher latitude cold water regimes. And this overall is going to reduce our seasonal effect. Again, there wasn't sort of a very clear signature in whether the ice was gaining or kind of consistent. But it is going against what we would expect to be happening in late August. And just again, to reiterate back to the first paper, in the second column there, your June, July, August storms, we can see the non-cyclone days predominantly reducing ice, about -5%, but the orange cyclone days are much closer to 0 and really reducing that seasonal effect. And so what we did next is, now that we've sort of defined these two prospective mechanisms for how the ice is changing with these winds and sort of motion into these changing ocean temperatures, we then went through an entire census of storms for August and September of 2007 to 2010. There were 26 storms total, and we found that 7 of them matched with the first case study and had predominantly southward blowing winds and an increase in ocean temperature along the marginal ice zone. 3 of them were similar to the second case study that had predominant north winds and motion of ice into colder waters. This, however, then leaves 16 storms still uncategorized that we still don't know a whole lot about. And so to sort of summarize the variations in these storms, we plotted some composite time series. And so this is what we're kind of thinking is going to be our typical response. And so first we have the 7 of our southward warming storms. And so plotted on top is fraction of total area from a week prior to the storm. And we can see once you average all 7 of these storms together, there's a very clear decline in sea ice from the cyclone response. And then the winds also are predominantly southward, and there's not a huge spread in these wind speeds. They're pretty consistent throughout the whole duration. And sea surface temperature anomaly, again, the ice starts out in these cooler waters and then increases and moves into these warmer waters. Next, if we look at our 3 of the case studies for northward cooling that match up with the second case study I showed, again, the response isn't as well defined as our first case study. There is a bit of an increase in sea ice in the top plot, but it is pretty constant throughout the time series, and it's not super well coupled with the start of the cyclone. Again, the wind is still a little variable. The sort of northward effect isn't necessarily as strong as the southward blowing effect. And the sea surface temperature anomaly, this one's pretty well defined. It starts out high and then decreases. But again, we're only averaging 3 storms. There is a bit more sort of unknown going on with these sort of fewer number of storms. And then lastly are 16 uncategorized. And this overall doesn't show much. There is pretty much no trend in sea ice area. The winds, too, have probably the highest variance, the highest spread among them. And then the sea surface temperature anomaly as well kind of all averages out. And so we still have a lot of work to do to kind of begin to parse through these and identify maybe even more potential mechanisms than just these 2 from the case studies that we've been looking at so far. And so just to kind of summarize, what do observations tell us about mechanical impacts of storms? And so here we identified these 2 potential sea ice responses, where you have enhanced winds driving sea ice southward into warmer water, leading to a pretty clear signal of ice loss. And then we have enhanced winds driving sea ice northward into cooler ocean, which then helps work against your sort of seasonal ice loss. But these 2 mechanisms only account for less than half of the responses within August and September over these 3 years. And there's a lot more variability in our second proposed mechanism. Again, maybe just because we don't necessarily have the case studies to back it up. And going to the conversation before, we anticipate winds being the primary influence. But there are a good number of limitations to this in that we are only looking primarily at 2 variables, the wind and ocean temperature. You know, we're not looking at ocean currents. We're not looking at the effects of waves or, you know, anything else that could potentially change our sea ice area. And so, kind of moving forward, one of the first things we want to look at is potentially dividing the storm into these two regions, because as we saw with a lot of these composite effects, a lot of the wind variables were hovering near zero because, you know, you're kind of averaging out the two sides of the storm. And so if we want to specify exactly the changes happening, we're going to have to look at these two regimes separately, because they do kind of have these competing effects, as we saw kind of with the sea ice concentration, creating that dipole. And so I think in doing that, we're going to try and find more trends in our sort of uncategorized storms, because, you know, we were only looking at, you know, the southward blowing winds and the increase in ocean temperatures, but there are, you know, maybe kind of the crisscross of that where, you know, you're going to have ice flowing kind of maybe in a different direction, and, you know, there's all these remaining unknowns, and hopefully by being a little more specific in our analyses, we can attempt to find these remaining trends. And lastly, we're going to look at the role of storms that occurred sequentially. And so, again, here, these two case studies that we looked at are kind of these standalone cases where we're able to compare pretty clearly against the climatology about what we were kind of anticipating to happen versus what actually did happen as the cyclone passed through. But if there are two storms that are kind of one after each other, we might be looking into the effect of kind of like a preconditioning where one storm can, you know, maybe compact the ice, move the ice into cooler waters, for example, and that could sort of reduce the effect of the secondary storm. And so throughout my talk, I sort of pretty much ignored the second question in its entirety. Is the mechanical effect enhanced by cloud radiative effects? And again, much like the wind and ocean temperature interactions, the role of clouds and precipitation is also quite complicated and quite tangled in with this mess of, you know, whether it can help enhance our mechanical effect or kind of work against it. And so just as an example, on the left here is an example of, so the first plot shows the cloud fraction, comparing two different events. And so when you look at this region where the clouds aren't present, it is coupled with an increase in downwelling shortwave radiation, which is going to lead to enhanced melt of the ice. And that's kind of counter to a secondary study looking at cloud effects over the Greenland ice sheet, showing that the net cloud forcing is a positive and increasing. And so we're sort of comparing, you know, if the additional clouds, you know, are going to warm, or if we're kind of trying to explain a decrease in sea ice, would a lack of clouds actually do that, due to increasing the short wave by not having clouds present? And so overall, there's just a lot of complications in not only the cloud effect here, but also with the wind effects as well. So that's my talk. Thank you. Any questions? Yeah, Ian.
Might be tangential, but do you happen to know if there's any evidence of these storms producing reductions in sea ice thickness through wind shear, frictional heating, something like that?
Yeah, so that's definitely something that we considered, but as you're probably aware, the satellite record on sea ice thickness isn't super well defined. So I don't know right away if there is that sort of immediate link. It would make sense that you would expect the storms to kind of, like you mentioned, the wind shear of the ice, particularly in the marginal ice zone as well. There is that kind of destruction And again, that's kind of another limitation of just looking at these effects here. You know, we're not getting the wave erosion, which will also influence the thickness. So in terms of using observations, that we don't have a super good idea.
And did it consider regional variabilities and topographic impacts? It seems like, depending on where you are in the Arctic, it can be quite important to consider any points of the ice or any topographic impacts coming through there.
Yeah, so location is definitely something I want to consider as I go through kind of those remaining storms. Topographically, again, I don't have a super good handle on that. I was thinking, especially with that second case study, we can go all the way back. You know, it's in a region that is, you know, dominated by these cooler waters, whereas the first case study, we do have kind of the intrusion of warm waters here. So location definitely plays a role, but I don't think I'm answering your question specifically about, you know, topography, because again, I'm not entirely sure how that would influence. All right, yes, Zoe.
Interesting thought. Have you thought about looking at or considered the impact of translational speed of how fast the cyclone is moving, and whether that might be one reason why you can't categorize it, just like translational of it?
Yeah, I mean, that's not something I thought of, but yeah, that definitely makes a lot of sense. And I think it's something we kind of hope to quantify sort of in discussing this sea ice area, like the impact area of the storm. But yeah, that's definitely something kind of moving forward.
I have a clarification question. So in this area, how much of the sea ice is like continuous versus like broken up, you know, and how big are these sea ice sheets? You know?
Yeah, so that's the kind of the main reason why we're defining this marginal ice zone, where anything greater than 80% is kind of where you'll see a kind of continuous sort of full cover, sort of near the central of the Arctic, and then around the edges is where you're going to have a lot more of that broken up ice that's a lot easier to move, and that kind of thing.
Do you mind going back to the slide where you described each of the case studies? I feel like I missed like what the relative anomaly was and how that relates. So like, I guess my question is the relative anomaly the difference from the expected sea ice loss based on that daily average from 2000 to 2019, or is it the loss just from that relative to just that year of 2010?
Yeah, it's the first one. It's
Okay.
kind of relative to the climatology.
Okay.
Yeah. But yeah.
Yeah, I was just wondering, it's really interesting, thanks for an interesting talk. The decrease in the daily sea ice area like shown here, and then shown for I think the 7 cases you looked at, seems to precede the cyclone event.
Yeah.
And so I'm kind of curious, does the removal of ice in a given region, it seems like it's about 5 to 7 days before the cyclone event occurs, help to set up the boundary layer so you have enhanced barochronicity so that introduces the possibility of a cyclone developing in that region. So you move the ice sheet northward a little bit because you decrease the ice area. Cyclones can develop along that boundary maybe more readily due to this greater barochronicity, horizontal temperature gradient. And then that can lead to further loss of ice because you have a cyclone. Is that a possible sequence?
Yeah, that definitely makes sense to me, especially, yeah, it is interesting how the decline does start kind of a little bit before when you would expect it to. So yeah, I would say that's...
Along those lines, it might be that we're picking the strongest cases. So these are going to be strongly forced. And if they get an assist in the boundary layer from a predecessor, recession of the ice, that might help them to really take shape as, sub 984 lows. And so I wonder if there isn't some kind of interaction there. And maybe if we looked at a census that had a less intense threshold, that might disappear. That's an interesting question. It's really interesting.
Yeah, hey there. This was a really interesting thought, and that got me thinking that I would think that if there's a storm, there might be some Ackermann topping going on, which could lead to bottom sea ice melt. I'm not sure whether that would be the case or not, but if there is, do you think that we could somehow untangle the ice loss because of the winds and because of the bottom sea ice loss somehow?
Yeah, I mean, definitely in some of the papers I've read, that are using more like models or looking a little bit more specifically into these ocean variables that you're bringing up, they have sort of looked at exactly what you mentioned, kind of the bringing up of warm water against the bottom, leading to bottom melt. And so that's definitely, again, another thing that we could analyze moving forward, and something that has been addressed in the literature as well as a viable mechanism. Yes, Julia.
So this could perhaps an open-ended question, something that I'm like still trying to figure out how to ask. But I'm wondering if you can comment on the radiative heat or cooling effects. So we're perhaps the diurnal cycle. So like how these impacts may be changing from day to night, and how that can be impacting storm development, which can be coupled to the changes in the sea ice. So I'm just, as I'm thinking about it, I imagine that might be quite complex and has contributing to the extent of how radiative impacts.
Yeah, so I mean, diurnal cycles isn't something, again, that's a little outside the scope here. But yeah, I mean, overall, I think looking at these cloud effects is that they're just really small, especially compared with kind of the winds being super strong in these storm events. But yeah, I think definitely that's something to look into as well, is how everything is coupled together. Yeah.
Yeah, just I imagine the radiative heating and cooling will be changing from day to night, not just like both from the clouds and from the sea ice itself. And yeah, the way that the clouds are impacting the sea ice is evolving.
Just to point out though, this is summertime, so the sun is up all day.
Oh, okay.
It's not, but that's not to say there's no diurnal effect. It does because they go up and down, but just keep in mind that the short wave doesn't go away at night, so it's not quite as dramatic as it is at lower latitudes. But then, yeah, it is a complicated problem, and it's a good question. So.
Hannah.
Okay, well, I'm a tropical person, so I'd be curious to see if you thought about the impact of, if some of these tropical cyclones had tropical origins, and whether or not that would influence how it interacts with the ice and
Yeah.
just since you're looking at August, like in that area, sometimes cyclones will have tropical origins, so I know that's not what you look at here, but that's curiosity of mine.
Yeah, I mean, I think that will definitely play in as I begin to kind of parse through even more of these cases, looking at exactly where they are and where they came from as well.
Well, this event here actually had a really pretty impressive tropical plume that came across the Mediterranean, the August 16th case. So all that cloud mass that's on the eastern side of the storm, you can see is connected to a strip of low PV that comes from the deep subtropics, right across North Africa. And I think Ian, and you showed it, Ian has the water vapor, integrated water vapor, total column water vapor in that storm is substantially larger than in the next one that comes 10 days later. And you can kind of see where it's coming from, roughly. It's better in the PV. So there is perhaps some connection in these stronger events. I think that's true.
Yeah.
I was going to point out your categorization between the northward and the southward sort of categorizations. That gave a thought to me of depending on where the cyclone lies in your sort of cyclone family or your Rossby wave range would matter. If the low has a high pressure out in front of it, then you would expect that northerly component to dominate. If it has a weak anticyclone behind it, then it's not going to have as much of a northerly on the backside. Whereas if the high is on the upstream side, you would expect that to reverse. So there might be a dynamic thing going on there too, where it's the position of the storm and a train. And then I think goes to the idea of looking at the storms in succession. So I think that's pretty cool.
actually, I was gonna say, so this composite work is very new, but maybe that's the next step, is once we do have a classification of storms, then we can come back and say, okay, now let's look at what the synoptic setup is for, you know, the ensemble of type 1 and type 2 storms, or whatever it is. I think that's, yeah.
And I think, I could just say, one other variable that's really interesting, or I should say a matrix of variables, is proximity to the ice edge and then precipitation type. Because if you're dropping snow on the ice as opposed to rain on the ice, it's a whole different ballgame, it would seem to me, not only instantaneously, but in the long term after the storm goes by, with the sun being up as it is.
So lovely talk, I'm loving all the interest in this. Okay, a couple things. Yes, Michael, ice does move well into the woods. So that's pretty standard. Two questions. So one, how come the 984 millibar limit for storm detection, is that just kind of deep enough relative to some sort of average? Like, why is that the number?
I mean, yeah, I think that was the cutoff that we used in sort of that, yeah, it kind of fit most of these cases. I'm not sure if Ian put this census together, yeah.
We just wanted to look at, we first wanted to look at the most intense events, with the suspicion that they'll have more mechanical effect, and they may have a bigger cloud head, and will magnify to whatever extent the magnification allows, the cloud radiative effects. So we thought we'd just start with big storm.
No, that makes sense, and I was just curious. That would be the right number. So, and then my other question, and you may not be able to answer this, so don't feel like you have to, kind of a two-parter here, becoming that person. So first off, like, do you have some sense of what the net effect on sort of the summertime parts of sea ice is based on what these storms do? Do you have some sense of where they melt a little bit in the marginal ice zone, and maybe they don't? But does that average out, or does it actually matter in comparison to this total summer melt that we see in the beginning? And the second part related to that is how do you expect it to change as we continue to lose ice in the Arctic and as we move toward ice-free summer in the Arctic? And I know that's a lot, and if you're like, I have no idea, I haven't thought about it, that's totally okay.
Yeah, I guess that kind of answered, I think, the second question first. As I think there's less ice, you're going to see a lot, kind of maybe an expansion of this marginal ice zone where it's going to be a lot thinner, a lot more vulnerable. And so I do think a lot of these effects are going to just be amplified overall. That's, again, sort of my intuition there. And then your first question, do you mind summarizing again real quick?
Yeah, so sort of what is the net effect basically of the storm on the ice in terms of melting versus not? Is it like a sort of, does it average out to something like there's slightly more melt because of the storms, maybe slightly less, or nothing, or do you have any idea what that looks like in that census during the summer?
Yeah, I mean, I think again that kind of is case to case. There's just so much variability. I mean, looking at our composite, we did see almost double the amount of ice loss events compared to the gain events. But again, that still leaves half the storms. If we look at our composite averages for uncategorized, right, it kind of does all average out for our remaining storms. But the effect of the 7 that we did identify is pretty large. We're losing, it's going down to almost half the ice amount that it started with in these regions. And so I guess for those cases, in comparison to the climatology, we are seeing a lot more of that enhanced melt. But yeah, I guess my answer is kind of a non-answer, that it depends. And for the ones that we did identify, the loss does seem to be pretty dominant.
I think this is where this is going. We just haven't taken the ratio. You're just saying,
Kind of what I figured.
yeah, basically take this and divide it by the climatology and see what the fraction.
I'm just
Yeah, it's as simple as doing that. I think we just haven't actually done it. So I think we're close to being able to do that. It's a good question to answer.
I think another way to go after that might be to look at years that are close to each other but have vastly different circulations. Like the summer 2016 has a lot more of these 984 cyclones in it than did the summer of 2010. There were only a few then. And they're close enough in time that one doesn't expect that the warming has exaggerated to such an extent that 16 is a vastly different year than 10 from that perspective. But from every other perspective, it could be really different. One of the manifestations of those differences might be the number of storms. So it might be cool to compare the ice loss in 16 to the ice loss in 10 and begin to ask it from that larger scale, longer time scale perspective, as opposed to or in conjunction with individual storms and their effect, you know.
In the given year, because we know that there's times where the summer ski ice loss is huge, versus not, but if that's kind of the direction you're going, that's
Yeah, 2012 was the big year, of course, and it had this giant storm in August. But it didn't have many other storms that year, so you couldn't really blame it on the storms. But if 16 didn't break that record, there's something else that kept it from doing so. You know, it's hard to really separate them all.
Well, of course, right?
That's a tough question.
Yeah, do you think that there's like, basically, there's kind of a radiative preconditioning before you even get to the storm? So it could matter, like, not just how many storms you have, but, or I mean, that does matter, but basically how late in the year it is, or where in the year it is, and how, you know, the radiative preconditioning before the storm. So like if you have, you might have thicker or thinner sea ice versus basically the interval of all the radiative conditions leading up to that.
Yeah, I think there's definitely a comparison there. So this is just for late summer storms in August and September. But I think if we were to look at, you know, earlier storms in June and July, and I think some of the papers I showed in the beginning did that as well, you did see a pretty significantly different response, where maybe there wasn't as much melt in response. Probably exactly what you're saying, because the ice, you know, is a little bit thicker, and you don't have that accumulated melt throughout the remainder of the summer. So, yeah, that's again something to kind of consider if we kind of expand outside of our late summer domain right now.
Yeah, I should add too that we should be able to expand the period, as John, you mentioned 2012 and 2016.
Yeah.
We are about to get radiation data generated for that whole period in 2018. So we should be able to expand this climatology, get more cases into these composites, and start to maybe even separate out the thicker, thinner ice, the preceding conditions. It's just this was a pretty limited data set, is mostly because of the CloudSat problem. Like we only had 4 years of CloudSat data to work on, but we will have more. So anyway, that was a great discussion after a talk. I love when we can have seminars like this. So let's thank Claire again for making